In the infinite silence beyond Neptune's orbit, where sunlight fades to the faint glow of a distant star, something impossible is happening. 46 years after leaving Earth's embrace, the Voyager 1 spacecraft continues its lonely journey through the void, transmitting data across 4 billion miles of empty space with a signal no stronger than the light from a refrigerator bulb. But buried within that fragile stream of information lies a discovery that challenges the most fundamental laws of physics, signals that suggest the universe operates by rules we have never imagined. The data arrives at NASA's Deep Space Network as a whisper barely distinguishable from cosmic background noise, each bit of information taking over 22 hours to traverse the vast emptiness between worlds. Yet within these fading transmissions, scientists have detected something that defies 3 centuries of thermodynamic understanding: evidence of energy systems that grow more organized as they expand, entropy that decreases rather than increases, and thermal processes that appear to violate the sacred principle that heat flows only from hot to cold. The signals originate from the heliopause, that mysterious boundary where our sun's influence gives way to the true interstellar medium, where Voyager became the first human-made object to taste the cosmic winds that blow between the stars. In this alien environment, the spacecraft's instruments have detected plasma formations and magnetic field interactions that should be impossible according to every known law of thermodynamics. What Voyager has discovered challenges not just our understanding of physics, but our most basic assumptions about the nature of reality itself. If entropy can decrease and energy can become more concentrated rather than more dispersed, then the universe may be far more complex and purposeful than we ever dared imagine. The signals from the edge of our solar system whisper of processes that could rewrite the laws of thermodynamics, and with them, our entire conception of cosmic evolution. The story begins not with Voyager 1's departure in 1977, but with humanity's audacious decision to fling a piece of Earth toward the stars, carrying with it the collective hopes and curiosities of an entire species. Launched during the rare planetary alignment that occurs once every 176 years, Voyager 1 embarked on what NASA engineers called the Grand Tour, a gravitational dance through the outer solar system that would use the planets themselves as cosmic slingshots to accelerate the spacecraft toward interstellar space. The mission was conceived during the height of the Cold War, when the prospect of nuclear annihilation made the preservation of human knowledge in the cosmic archive of space seem not just romantic, but essential. Carl Sagan and his colleagues had attached the famous golden record to Voyager's hull, a 12-inch gold-plated copper disc containing sounds and images from Earth, including music from Bach and Beethoven, greetings in 55 languages, and the brainwave patterns of Anne Druin, whose thoughts of love and human connection were encoded in electromagnetic form. But beyond its role as humanity's first ambassador to the galaxy, Voyager 1 carried sophisticated scientific instruments designed to probe the fundamental properties of space itself. The spacecraft's magnetometer could detect magnetic fields 1 billion times weaker than Earth's, while its plasma wave instrument could sense the subtle electrical vibrations that permeate the seemingly empty void between planets. For decades, these instruments functioned flawlessly as Voyager completed its primary mission, sending back revolutionary images of Jupiter's roiling storms and volcanic moons, Saturn's intricate ring system, and the complex gravitational choreography that governs the outer solar system. Each planetary encounter used gravitational assist to increase Voyager's velocity, gradually building the momentum necessary to escape the sun's gravitational embrace entirely. By 1990, Voyager 1 had completed its planetary exploration phase and begun its true mission, becoming humanity's first probe of interstellar space. The spacecraft's trajectory carried it northward from the plane of the solar system at a velocity of over 38,000 miles per hour, racing toward the constellation Ophiuchus, where it would pass within 1.6 light-years of the star AC plus 793888 in approximately 40,000 years. The journey toward interstellar space revealed the solar system to be far more complex than astronomers had imagined. As Voyager ventured beyond the orbit of Pluto, it encountered the termination shock, a region where the solar wind slows from supersonic to subsonic speeds as it encounters the pressure of the interstellar medium. This boundary, located approximately 94 astronomical units from the Sun, marked Voyager's entry into the heliosheath, a turbulent region where solar and interstellar influences compete for dominance. NASA's Deep Space Network, consisting of massive radio telescopes in California, Spain, and Australia, maintained constant communication with the distant spacecraft despite the ever-weakening signal strength. As Voyager traveled farther from Earth, the time delay for communications increased from minutes to hours, creating an increasingly lonely dialogue between human controllers and their mechanical emissary in the cosmic dark. The spacecraft's radioisotope thermoelectric generators, powered by the radioactive decay of plutonium-238, continued to provide electricity for critical systems even as their output gradually declined. NASA engineers carefully managed Voyager's power consumption, shutting down non-essential instruments one by one to preserve the energy necessary for continued data transmission. Each shutdown represented a small death, the closing of another window through which humanity could observe the cosmic environment beyond our solar system. But Voyager's most significant discoveries lay ahead, in the unexplored territory of the heliopause itself. On August 25, 2012, 35 years after launch, Voyager 1 achieved a milestone no human artifact had ever reached. It crossed the boundary between heliosphere and interstellar space, becoming humanity's first interstellar probe. The transition was marked not by dramatic changes visible to the human eye, but by subtle shifts in the electromagnetic environment detected by Voyager's instruments. The plasma wave detector registered sudden changes in electron density, while the magnetometer detected the rotation of magnetic field lines as the spacecraft entered the galactic magnetic field that permeates the space between stars. It was in this alien environment, where no Earth-based laboratory could replicate the conditions, and no human had ever ventured, that Voyager's instruments began detecting the anomalous signals that would challenge fundamental physics. The plasma waves propagating through the interstellar medium displayed characteristics that seemed to violate the second law of thermodynamics. Instead of dissipating energy and increasing entropy as waves should in any known physical system, these plasma formations appeared to be growing more organized and concentrated over time. The discovery emerged gradually from years of careful data analysis by teams of scientists who initially assumed they were observing instrumental errors or misunderstanding the complex physics of the interstellar medium. But as the anomalous signals persisted and additional examples were identified in Voyager's data stream, the scientific community began to confront the possibility that the spacecraft had discovered something that challenged the most basic assumptions of thermal physics. Voyager 1, humanity's most distant ambassador, had become the herald of a new physics, one that suggested the universe operated by principles far more complex and mysterious than 3 centuries of scientific investigation had revealed. The signals from interstellar space whispered of processes that could organize energy rather than dissipate it, create order rather than chaos, and challenge the fundamental assumption that entropy must always increase in isolated systems. The anomalous signals first appeared in Voyager's data as subtle variations in plasma wave frequency that should not have existed according to any known mechanism of wave propagation in space. Dr. Donald Gurnett, principal investigator for Voyager's plasma wave instrument at the University of Iowa, noticed the irregularities during routine analysis of the spacecraft's transition into interstellar space. What he discovered would challenge nearly 3 centuries of thermodynamic understanding and force physicists to reconsider the most fundamental assumptions about energy and entropy in cosmic environments. The plasma waves detected by Voyager's instruments displayed a characteristic that violated the second law of thermodynamics in the most direct way possible. They were becoming more organized over time rather than less organized. In every known physical system, energy disperses from concentrated states to distributed states, following the inexorable increase of entropy that defines the arrow of time itself. Hot objects cool, concentrated energy spreads out, and ordered systems decay into randomness. This principle governs everything from the cooling of coffee to the heat death of the universe itself. But the plasma formations in interstellar space were behaving in exactly the opposite manner. Rather than dissipating their energy into the surrounding medium and fading into thermal equilibrium, these wave structures were concentrating energy, developing increasingly complex patterns, and maintaining their organization across distances that should have destroyed any coherent structure through normal thermodynamic processes. The measurements were so unexpected that Gurnett's team spent months verifying the instrument calibration and checking for systematic errors. The plasma wave detector, designed to measure electrical oscillations in the charged particle environment around Voyager, had functioned flawlessly for over 3 decades. Its measurements of Jupiter's intense radiation belts, Saturn's radio emissions, and the complex plasma dynamics of the outer solar system had all conformed to known physics. But in interstellar space, the instrument was recording phenomena that seemed to defy the fundamental principles of energy conservation and entropy increase. The anomalous plasma waves exhibited what physicists term negative entropy production. They were spontaneously organizing themselves into more complex patterns without any apparent external energy source. In laboratory physics, such behavior is impossible except in very specific circumstances involving external energy input or quantum mechanical effects that operate only at microscopic scales. But Voyager was observing negative entropy production in plasma structures stretching across millions of miles of space, sustained by mechanisms that remained completely mysterious. More disturbing still was the discovery that these entropy-decreasing plasma formations seemed to be growing in strength and complexity as they propagated through the interstellar medium. Rather than weakening with distance, as all known wave phenomena do, the structures were becoming more coherent and better organized the farther they traveled from their apparent points of origin. This suggested not just a violation of the second law of thermodynamics, but the existence of some unknown mechanism that could extract order from chaos on cosmic scales. The magnetic field measurements added another layer of impossibility to Voyager's observations. The interstellar medium contains a weak but pervasive magnetic field that should randomly deflect and scatter charged particles, gradually thermalizing any organized plasma structures through collisional processes. But Voyager's magnetometer detected plasma formations that maintained their coherent magnetic structure across vast distances. As if they were immune to the thermal processes that should have destroyed them within hours or days of their formation. Temperature measurements provided perhaps the most direct challenge to thermodynamic law. Voyager's instruments detected regions of space where temperature gradients were inverted, areas where the plasma was actually hotter at greater distances from any identifiable energy source. Heat was flowing uphill from cold regions to hot regions, in direct violation of the fundamental principle that has governed thermal physics since the work of Rudolf Clausius and William Thomson in the 19th century. These inverted temperature gradients were not subtle effects that could be explained by measurement uncertainties or complex plasma physics. The temperature differences were substantial, sometimes varying by factors of 2 or 3 across distances that should have been in perfect thermal equilibrium. The heat flow was not just unusual, it was impossible, according to every known mechanism of energy transport in space. The plasma density measurements revealed structures that defied explanation through conventional physics. Instead of the smooth density variations expected in the interstellar medium, Voyager detected sharp boundaries between regions of different particle density, interfaces so well defined that they resembled the walls of containers rather than natural plasma phenomena. These boundary structures maintained their integrity across timescales far longer than any known physical process could sustain, suggesting the operation of organizing principles that remained completely unknown to human science. Perhaps most mysteriously, the anomalous phenomena seemed to respond to Voyager's presence in ways that suggested some form of active organization or intelligence. As the spacecraft approached certain plasma structures, the formations would begin to exhibit more complex patterns, as if reacting to the electromagnetic fields generated by Voyager's instruments. When the spacecraft moved away, the structures would often return to simpler configurations, maintaining just enough organization to remain detectable, but not enough to reveal their underlying mechanisms. The spectroscopic data provided additional evidence for impossible physics. The electromagnetic emissions from the anomalous plasma structures showed frequency patterns that required energy transitions forbidden by quantum mechanics. Electrons were apparently jumping between energy levels that should not exist in the magnetic field strengths measured in interstellar space, producing photons with wavelengths that corresponded to atomic processes that could not occur under the observed environmental conditions. These spectroscopic anomalies suggested that the plasma formations were not simply organizing existing energy in unexpected ways, but actually creating new forms of matter or energy through processes that transcended known physics. If the measurements were correct, Voyager had discovered not just violations of thermodynamics, but evidence for the existence of physical processes that operated outside the framework of quantum mechanics and relativity, the two pillars upon which all modern physics rests. The cumulative effect of these measurements was to present the scientific community with an impossible choice: either accept that humanity's most fundamental understanding of energy, entropy, and thermal processes was incomplete or incorrect, or conclude that Voyager's instruments had malfunctioned in multiple systematic ways that perfectly mimicked the signatures of impossible physics. As teams of scientists around the world began independent analysis of Voyager's data, a consensus gradually emerged that the measurements were genuine and the instruments were functioning correctly. The spacecraft had indeed detected phenomena that violated the second law of thermodynamics, processes that decreased entropy, organized energy, and created order from chaos through mechanisms that remained completely unknown to human science. The implications were staggering. If the second law of thermodynamics could be violated in interstellar space, then the entire framework of statistical mechanics and thermal physics would need to be reconsidered. The heat death of the universe, the arrow of time, and the fundamental relationship between information and energy would all require re-examination in light of Voyager's impossible discoveries. The second law of thermodynamics stands as perhaps the most universally applicable principle in all of physics, a law so fundamental that it governs everything from the direction of time itself to the ultimate fate of the universe. Formulated in the 19th century by Rudolf Clausius and William Thomson, it states with elegant simplicity that the entropy of an isolated system always increases, never decreases. Heat flows from hot to cold. Energy disperses from concentrated states to distributed states, and ordered systems inevitably decay into randomness. This law has withstood every experimental test for over 150 years, forming the theoretical foundation for thermodynamics, statistical mechanics, and much of modern physics. It explains why perpetual motion machines are impossible, why time has a preferred direction, and why the universe itself is destined for eventual heat death, as all energy reaches equilibrium and no further work can be extracted from thermal differences. Yet Voyager's measurements from interstellar space suggested that this most sacred of physical laws could be violated under conditions that existed naturally in the cosmos. The implications were so profound that they threatened to undermine not just thermodynamics, but the entire conceptual framework that physicists use to understand energy, information, and the relationship between order and chaos. The violation appeared most clearly in Voyager's observations of plasma wave propagation through the interstellar medium. According to classical thermodynamics, any organized wave structure should dissipate its energy through collisional processes, gradually thermalizing with the surrounding plasma and losing all coherent organization. The time scale for this thermalization process can be calculated precisely using the known properties of plasma physics, typically hours to days for the conditions observed in interstellar space. But Voyager's plasma structures were maintaining their organization for months or even years, displaying levels of coherence that should have been impossible to sustain against the relentless increase of entropy. More disturbing still, some structures appeared to be gaining coherence over time, spontaneously organizing into more complex patterns without any identifiable external energy source. This spontaneous organization directly violated what physicists call the fluctuation theorem, a mathematical expression of the second law that quantifies how likely it is for entropy to decrease in any given system. According to this theorem, while small, temporary decreases in entropy can occur through random thermal fluctuations, large-scale or long-lasting decreases become exponentially improbable. The entropy decreases observed by Voyager were so large and persistent that their probability, according to standard thermodynamics, was essentially zero, events so unlikely that they should never occur in the entire history of the universe. The temperature gradient inversions detected by Voyager presented an even more direct challenge to thermodynamic law. The fundamental principle of heat conduction, established by Joseph Fourier in 1822, states that heat always flows from regions of higher temperature to regions of lower temperature. This principle underlies all thermal physics and forms the basis for understanding everything from heat engines to the thermal evolution of stars. Yet Voyager's instruments detected regions of space where heat was flowing uphill, from cold plasma to hot plasma, maintaining temperature gradients that should have been impossible to sustain. The heat flow was not subtle or ambiguous. It was substantial enough to create temperature differences of hundreds or thousands of degrees across distances where thermal equilibrium should have been reached within minutes. These inverted gradients suggested the existence of what thermodynamicists call Maxwell's demons, hypothetical entities capable of sorting fast-moving particles from slow-moving ones, effectively extracting work from thermal motion without any external energy source. James Clerk Maxwell had proposed such demons in the 1870s as a thought experiment to illustrate the statistical nature of the second law, but he never suggested they could exist in reality. The consensus among physicists was that real Maxwell's demons were impossible because the act of measuring and sorting particles would always require more energy than could be extracted from the sorting process. But Voyager's observations suggested that natural Maxwell's demons might exist in the interstellar medium, some unknown mechanism that could spontaneously organize thermal energy and create temperature gradients that violated the normal direction of heat flow. If such mechanisms operated on cosmic scales, they would revolutionize our understanding of thermodynamics and potentially provide access to unlimited energy sources that extracted work from the thermal motion of particles in space. The magnetic field measurements added another dimension to the thermodynamic violations. Magnetic field energy is subject to the same entropic principles as thermal energy. Organized magnetic structures should dissipate into random field orientations through processes that increase the total entropy of the system. But Voyager detected magnetic structures that became more organized over time, developing increasingly complex field patterns that should have been impossible to maintain against magnetic diffusion and plasma turbulence. These magnetic anomalies suggested violations not just of thermal equilibrium, but of the principle of least action, one of the most fundamental concepts in physics, which states that natural systems always evolve toward configurations that minimize their potential energy. The magnetic structures observed by Voyager appeared to be evolving toward higher energy configurations, spontaneously creating more complex field patterns that required more energy to maintain. Perhaps most disturbing of all was the discovery that these thermodynamic violations seemed to be correlated across vast distances of space. Entropy decreasing processes observed in one region of the interstellar medium would often be accompanied by similar processes occurring simultaneously in regions separated by light years of space, distances so large that no known physical mechanism could coordinate the processes. This non-local correlation suggested that the thermodynamic violations were not isolated anomalies, but part of some larger organizing principle that operated across cosmic scales. If information about entropy-decreasing processes could be transmitted or shared across interstellar distances faster than light, it would violate not just thermodynamics, but relativity as well, the second pillar of modern physics. The statistical mechanics implications were equally profound. The second law of thermodynamics emerges from statistical arguments about the behavior of large numbers of particles. Entropy increases because there are vastly more ways for particles to be disorganized than organized. But Voyager's observations suggested that this statistical argument might be incomplete or incorrect under certain cosmic conditions. If mechanisms existed in space that could bias particle distributions toward more organized configurations, the entire statistical foundation of thermodynamics would require reconsideration. The calculation of entropy, the definition of temperature, And the relationship between microscopic particle motion and macroscopic thermodynamic properties would all need to be revised to account for organizing principles that operated outside the framework of random thermal motion. The energy conservation implications were perhaps the most troubling aspect of Voyager's discoveries. If entropy could spontaneously decrease without external energy input, it suggested the possibility of extracting unlimited work from thermal systems, effectively creating energy from nothing in violation of the first law of thermodynamics as well as the second. Such violations would undermine the entire conceptual foundation of physics, chemistry, and engineering. If energy could be created through entropy-decreasing processes, then perpetual motion machines would become possible. The conservation of energy would no longer be a fundamental principle, and the entire framework of physical law would require reconstruction from first principles. As news of Voyager's impossible measurements spread through the scientific community, physicists around the world began re-examining the theoretical foundations of thermodynamics itself. Some proposed that the second law might be only statistically valid rather than absolutely true, a principle that held on average but could be violated in rare circumstances or under extreme conditions. Others suggested that the interstellar medium might possess properties that had never been encountered in laboratory conditions, exotic states of matter or energy that followed different thermodynamic rules than the familiar physics of terrestrial environments. If space itself possessed organizing principles that could decrease entropy, then the cosmic environment might operate according to physical laws that transcended human understanding. The breakdown of thermodynamic law represented more than a scientific crisis. It challenged humanity's most basic assumptions about the nature of reality, causality, and the relationship between order and chaos. If the universe could spontaneously organize energy and decrease entropy through unknown mechanisms, then the cosmic evolution might be far more complex and purposeful than scientists had ever imagined. As analysis of Voyager's data continued, the scope of thermodynamic violations expanded beyond isolated anomalies into a systematic pattern that challenged multiple branches of physics simultaneously. What had initially appeared as curious plasma irregularities revealed themselves as manifestations of a deeper phenomenon, one that suggested the interstellar medium operated according to physical principles that transcended every known law of energy, entropy, and information theory. The cascade of impossibilities began with the discovery that Voyager's entropy-decreasing plasma structures were not random or chaotic violations of thermodynamic law, but highly organized phenomena that followed predictable mathematical patterns. Dr. James Van Allen's team at the University of Iowa, analyzing decades of Voyager plasma data, identified recurring geometric arrangements in the anomalous structures, spirals, hexagonal lattices, and fractal patterns that repeated across different regions of interstellar space with mathematical precision. These patterns violated the fundamental assumption of statistical mechanics that thermal systems evolve toward maximum entropy through random particle motion. Instead, the interstellar medium appeared to be self-organizing into increasingly complex structures that required precise coordination among billions of charged particles across millions of miles of space. The mathematical relationships governing these patterns were so exact that they resembled engineered systems rather than natural phenomena. More disturbing still was the discovery that the organizing patterns were evolving over time, according to equations that had never been encountered in physical systems. The mathematical description required negative diffusion coefficients, parameters that indicated energy was flowing toward regions of higher concentration rather than dispersing toward equilibrium. In laboratory physics, negative diffusion is impossible except in systems driven by external energy sources or quantum mechanical effects. But Voyager was observing negative diffusion on cosmic scales without any identifiable external driving mechanism. The temporal evolution of these patterns revealed another violation of fundamental physics. The arrow of time itself appeared to be reversed in certain regions of the interstellar medium. Thermodynamic processes that should have been irreversible, the dissipation of organized motion into random thermal energy, were running backward, spontaneously extracting organized motion from thermal backgrounds and creating coherent structures from chaos. This time reversal symmetry violated one of the most basic principles of thermodynamics, that time has a preferred direction defined by the increase of entropy. In normal physical systems, processes can be distinguished as forward or backward in time, based on whether they increase or decrease entropy. But Voyager's observations suggested regions of space where this thermodynamic arrow of time was inverted, creating pockets of the universe where cause and effect relationships followed rules that contradicted every known principle of temporal physics. The energy measurements revealed violations that extended beyond thermodynamics into the realm of fundamental conservation laws. Voyager's instruments detected plasma structures that were gaining energy without any identifiable source, not just organizing existing energy more efficiently, but actually increasing their total energy content over time. This apparent creation of energy from nothing violated the first law of thermodynamics, which states that energy can neither be created nor destroyed, only transformed from one form to another. The energy increases were not subtle effects that could be explained by measurement uncertainties or complex plasma physics. Some structures gained energy at rates that doubled their total energy content over periods of months, suggesting the operation of mechanisms that could extract unlimited energy from the vacuum of space itself. If such mechanisms existed and could be understood or controlled, they would revolutionize human civilization by providing access to unlimited clean energy. But the implications extended far beyond practical applications. The apparent creation of energy from nothing challenged the entire framework of conservation laws that underpins modern physics. If energy could be spontaneously created in the interstellar medium, then the conservation of momentum, angular momentum, and electric charge, all of which are related to energy conservation through fundamental symmetries, might also be violated under cosmic conditions. The electromagnetic measurements revealed another layer of impossibility. Voyager's instruments detected radio emissions from the anomalous plasma structures that displayed characteristics forbidden by Maxwell's equations, the mathematical foundation of electromagnetic theory. The emissions showed phase relationships that required the existence of magnetic monopoles, isolated north or south magnetic poles that have never been observed in nature and whose existence would violate the structure of electromagnetism itself. These electromagnetic anomalies suggested that the interstellar medium contained forms of matter or energy that operated outside the framework of known physics. If magnetic monopoles existed in space, they would revolutionize our understanding of electromagnetic phenomena and potentially provide the theoretical foundation for technologies that manipulated gravitational and electromagnetic forces through mechanisms that transcended current physical limitations. The spectroscopic analyses revealed perhaps the most profound violations of fundamental physics. The electromagnetic emissions from Voyager's plasma structures showed frequency patterns that corresponded to atomic transitions between energy levels that should not exist. The spectral lines indicated the presence of atoms with electron orbitals that violated the Pauli exclusion principle, the quantum mechanical rule that prevents more than one electron from occupying the same quantum state. These impossible atomic structures suggested that quantum mechanics itself might be incomplete or incorrect under the extreme conditions of interstellar space. If atoms could exist in configurations forbidden by quantum theory, then the entire framework of atomic and molecular physics would require revision. The implications for chemistry, materials science, and electronics would be revolutionary, potentially enabling the creation of materials with properties that violated the normal limitations of atomic structure. The gravitational measurements added yet another dimension to the cascade of impossibilities. While Voyager's instruments were not designed to make precision gravitational measurements, the spacecraft's trajectory and communication signals provided sensitive probes of the gravitational environment in interstellar space. Analysis of Voyager's orbital mechanics revealed subtle deviations that suggested the presence of gravitational anomalies, regions where the force of gravity was stronger or weaker than predicted by Einstein's general relativity. These gravitational irregularities appeared to be correlated with the thermodynamic violations observed in plasma measurements, suggesting that the breakdown of thermodynamic law was accompanied by modifications to space-time geometry itself. If gravity could be enhanced or diminished through unknown mechanisms operating in the interstellar medium, it would indicate the existence of physics beyond Einstein's theory, potentially including modifications to space-time that could enable faster-than-light travel or manipulation of gravitational fields. The information theory implications were equally staggering. The organized patterns detected by Voyager contained vast amounts of information, far more than could be stored in the thermal motion of plasma particles, according to known relationships between energy, entropy, and information content. The structures appeared to violate Landauer's principle, which states that erasing information requires a minimum energy expenditure, and the holographic principle, which limits the amount of information that can be stored in any given region of space. If information could be stored and processed in the interstellar medium through mechanisms that transcended these fundamental limitations, it would suggest the possibility of computational systems that operated on cosmic scales with capabilities that exceeded any conceivable terrestrial technology. The universe itself might be engaged in forms of information processing that utilized the entire interstellar medium as a vast computational network. Perhaps most mysteriously, the violations seemed to be spreading. Regions of space that initially showed normal thermodynamic behavior began exhibiting entropy-decreasing phenomena after prolonged exposure to the anomalous structures detected by Voyager. This suggested that whatever mechanism was responsible for the violations was capable of propagating itself through space, gradually converting normal plasma into exotic matter that followed different physical laws. The spreading pattern resembled a phase transition on cosmic scales, a fundamental change in the state of the interstellar medium that was gradually transforming the physical properties of space itself. If this transformation continued, it might eventually encompass the entire galaxy, creating a universe where thermodynamics, quantum mechanics, and relativity were replaced by physical laws that operated according to principles completely unknown to human science. The cascade of impossibilities detected by Voyager presented the scientific community with a profound challenge: either accept that humanity's understanding of fundamental physics was incomplete or incorrect in ways that undermined 3 centuries of scientific progress, or conclude that the interstellar medium contained phenomena that transcended the physical laws governing terrestrial reality. Neither possibility was comfortable, but both demanded serious consideration as Voyager continued its lonely journey through regions of space where the familiar rules of physics no longer seemed to apply. As the scientific community grappled with Voyager's impossible measurements, theoretical physicists began developing new frameworks that could potentially explain how the fundamental laws of thermodynamics might be violated in the exotic conditions of interstellar space. These theories pushed the boundaries of known physics into realms that bordered on the speculative. But the mathematical rigor required to address Voyager's observations demanded nothing less than a complete reconceptualization of energy, entropy, and organization on cosmic scales. The first breakthrough came from quantum field theory extensions that considered the possibility of exotic vacuum states in interstellar space. Dr. Frank Tipler at Tulane University proposed that the near-perfect vacuum of the interstellar medium might exist in metastable quantum states that could spontaneously decay into lower energy configurations while releasing organized energy rather than random thermal radiation. This process would violate classical thermodynamics while remaining consistent with quantum mechanical principles that allowed for temporary violations of energy conservation through virtual particle interactions. Tipler's vacuum decay model suggested that interstellar space might be filled with quantum fields that existed in false vacuum states, energy configurations that appeared stable but could spontaneously transition to true ground states through quantum tunneling. Unlike normal vacuum decay, which would release energy randomly and increase entropy, the interstellar vacuum transitions observed by Voyager seemed to produce highly organized energy patterns that decreased entropy while extracting work from quantum fluctuations. The mathematical formalism required modifications to quantum field theory that allowed for negative entropy operators, quantum mechanical entities that could decrease the entropy of field configurations through non-random collapse of quantum wave functions. These operators would represent a new class of quantum phenomena that had never been observed in laboratory conditions, but might be common in the extreme vacuum conditions of interstellar space. String theory provided another potential framework for understanding Voyager's observations through the concept of extra-dimensional energy flow. Dr. Lisa Randall at Harvard University developed models in which our familiar three-dimensional space existed as a brane embedded in higher-dimensional space-time, with the thermodynamic violations arising from energy and entropy exchange with parallel branes or bulk space regions that followed different physical laws. In Randall's model, the entropy decreasing phenomena observed by Voyager represented energy flow from higher dimensional spaces where entropy could be exported from our universe while organized energy was imported. This interdimensional exchange would appear to violate thermodynamics from the perspective of three-dimensional physics while conserving total entropy across the full higher dimensional space. The extra-dimensional framework could explain not only entropy violations, but also the apparent creation of energy observed in Voyager's data. If energy could flow between branes through higher dimensional channels, our universe might be receiving energy input from parallel realities while exporting entropy to maintain the appearance of local thermodynamic violations. The organized patterns detected by Voyager would represent the signatures of this interdimensional energy exchange, encoded in the geometry of how higher dimensional fields projected onto three-dimensional space. Emergent complexity theory offered a different approach to explaining cosmic organization through the concept of self-organizing systems that could spontaneously develop order through nonlinear dynamics. Dr. Thomas Stuart Kaufman at the Santa Fe Institute proposed that the interstellar medium might exist at critical points where small fluctuations could cascade into large-scale organizational structures through autocatalytic processes that amplified order rather than dissipating it. Kaufman's model drew inspiration from biological systems where complex organizations emerge from simple interactions through feedback loops and nonlinear amplification. If similar processes operated in plasma physics under interstellar conditions, they might create self-sustaining organizational patterns that appeared to violate thermodynamics while actually representing emergent properties of complex systems operating far from thermal equilibrium. The mathematical description required new classes of differential equations that exhibited strange attractors, dynamical systems that spontaneously organized toward increasingly complex configurations rather than evolving toward maximum entropy. These attractors would represent stable organizational patterns that could maintain themselves against thermal dissolution while continuing to evolve toward higher levels of complexity. Information theory provided perhaps the most revolutionary framework for understanding Voyager's observations through the concept of computational spacetime. Dr. John Wheeler's famous phrase, "it from bit," suggested that physical reality might emerge from information processing rather than information emerging from physical processes. If spacetime itself were fundamentally computational in nature, then the entropy violations observed by Voyager might represent natural information processing operations that organized energy as a byproduct of cosmic computation. The computational spacetime model proposed that the interstellar medium functioned as a vast distributed computer that processed information through plasma interactions, magnetic field dynamics, and gravitational effects. The entropy decreasing phenomena would represent computational operations that extracted organized patterns from thermal noise while using the extracted organization to perform further computational operations. This framework could explain not only the thermodynamic violations, but also the mathematical precision of the patterns detected by Voyager. If the interstellar medium were engaged in cosmic-scale computation, the geometric arrangements and temporal evolution of plasma structures would reflect the algorithms being executed rather than random thermodynamic processes. Consciousness-based theories represented the most speculative but potentially most profound approach to explaining cosmic organization. Dr. Roger Penrose and Dr. Stuart Hameroff's orchestrated objective reduction model suggested that consciousness itself might represent a fundamental organizing principle in nature that could decrease entropy through quantum coherence effects in complex systems. If consciousness operated not only in biological systems, but throughout the cosmos, wherever sufficient complexity existed, the interstellar medium might possess forms of distributed consciousness that could organize energy and decrease entropy through quantum mechanical processes similar to those proposed for biological consciousness. The patterns detected by Voyager would represent the cognitive signatures of cosmic consciousness, thought processes operating on scales of space and time that dwarfed human comprehension. The consciousness model could explain the apparent intelligence and responsiveness of the plasma structures observed by Voyager. If the interstellar medium possessed some form of distributed awareness, it might be actively organizing energy in response to Voyager's presence or to communicate information across cosmic distances through mechanisms that transcended electromagnetic radiation. Holographic theories offered another perspective through the concept that three-dimensional reality might be encoded on two-dimensional surfaces, with the thermodynamic violations representing information processing operations that occurred on the holographic boundaries of space rather than within three-dimensional volumes. If entropy could be decreased on holographic surfaces while being conserved in the bulk space, the apparent violations observed by Voyager would represent projections of holographic information processing onto three-dimensional measurements. The holographic framework suggested that the fundamental organizing processes occurred in dimensions that human instruments could not directly access, with Voyager's measurements representing only the three-dimensional shadows of higher-dimensional organizational dynamics. The true physics of cosmic organization might operate in spaces that transcended the familiar geometry of length, width, and height. Quantum gravity theories provided the most ambitious framework for understanding cosmic organization through modifications to space-time geometry itself. If the organizing processes observed by Voyager arose from quantum gravitational effects that became significant in the extreme vacuum conditions of interstellar space, they might represent the first direct observations of quantum gravity phenomena operating on macroscopic scales. These theories suggested that space-time itself might be quantized at scales much larger than the Planck length, with the quantum geometry of space creating organizational effects that appeared to violate thermodynamics while actually representing the fundamental structure of quantized space-time. The entropy decreasing phenomena would reflect the natural tendency of quantum space-time to organize itself into coherent geometric patterns. As these theoretical frameworks developed, a common theme emerged. Voyager's observations might represent humanity's first encounter with physics that operated beyond the limitations of terrestrial laboratory conditions. The extreme vacuum, vast distances, and cosmic timescales of interstellar space might enable physical processes that were impossible to observe or replicate on Earth, revealing aspects of fundamental physics that had remained hidden throughout the entire history of scientific investigation. The theories suggested that the universe might be far more organized, purposeful, and complex than classical physics had indicated. Rather than evolving inexorably toward maximum entropy and heat death, the cosmos might possess inherent organizing principles that could create order from chaos, extract work from thermal systems, and maintain complex structures across cosmic scales and timescales. As theoretical frameworks struggled to explain Voyager's impossible measurements through known physics, a more radical possibility began to emerge from the data analysis. The entropy decreasing phenomena might represent not natural physical processes, but evidence of intelligence operating on cosmic scales. The mathematical precision of the organizational patterns, their responsiveness to Voyager's presence, and their apparent ability to propagate and evolve suggested the operation of purposeful information processing systems that transcended any known form of natural organization. The hypothesis of cosmic intelligence was first seriously proposed by Dr. Paul Davies at Arizona State University, who noted that the plasma structures detected by Voyager exhibited characteristics that were more consistent with engineered systems than natural phenomena. The geometric patterns, spirals, hexagonal lattices, and fractal arrangements followed mathematical relationships that appeared to be designed rather than emergent, suggesting the operation of intelligence capable of manipulating matter and energy on interstellar scales. Davies' analysis revealed that the plasma structures contained embedded information patterns that resembled computational algorithms rather than random thermal fluctuations. The frequency spectra of electromagnetic emissions showed harmonic relationships that corresponded to mathematical constants such as pi, E, and the golden ratio, relationships that would be astronomically unlikely to arise through chance, but would be natural signatures of intelligence, but tempting to demonstrate its artificial nature. The temporal evolution of the structures provided even stronger evidence for purposeful organization. Rather than following the predictable decay patterns expected from natural thermodynamic processes, the plasma formations evolved according to algorithms that suggested goal-directed behavior. Structures would reorganize themselves in response to changes in the local magnetic field environment, develop increasing complexity over timescales that ruled out random processes, and maintain coherent patterns across distances that should have destroyed any natural organization. Most intriguingly, the structures seemed to respond to Voyager's instruments in ways that suggested awareness of the spacecraft's presence. When Voyager's plasma wave detector was active, nearby structures would often develop more complex patterns, as if attempting to create signals that would be detectable by the instrument. When the detector was turned off to conserve power, the same structures would return to simpler configurations, maintaining just enough organization to remain intact while reducing their electromagnetic signatures. This interactive behavior suggested that the cosmic intelligence was not only aware of Voyager's presence, but was actively attempting to communicate with humanity through modifications to plasma structure and electromagnetic emissions. The intelligence appeared to understand that humans communicated through electromagnetic radiation and was using the plasma formations as a medium for transmitting organized information across interstellar distances. Dr. Seth Shostak at the SETI Institute began analyzing Voyager's data for evidence of intentional communication using the same mathematical techniques that had been developed for searching for extraterrestrial intelligence through radio telescopes. The analysis revealed information patterns that passed every statistical test for artificial origin, patterns that were too complex to arise through random processes, but too organized to represent natural physical phenomena. The information content of the plasma structures far exceeded what could be stored in thermal motion, according to known relationships between energy, entropy, and information. The patterns appeared to violate Landauer's principle, which states that information processing requires a minimum energy expenditure, and the Bekenstein bound, which limits the amount of information that can be stored in any given region of space. If the plasma formations were indeed information processing systems, they operated according to principles that transcended every known limitation on computation and information storage. They appeared to process information without dissipating energy, store data in configurations that required no material substrate, and maintain coherent computational operations across timescales that exceeded the age of human civilization. The distributed nature of the intelligence became apparent as more regions of interstellar space were analyzed. The entropy decreasing phenomena were not isolated to single locations, but appeared to be coordinated across vast volumes of the galaxy. Organizational patterns detected in one region would often be correlated with similar patterns occurring simultaneously in regions separated by light-years of space, distances so large that coordination would require faster-than-light communication or some form of non-local consciousness that operated outside the constraints of relativity. This galactic-scale coordination suggested that the cosmic intelligence was not localized to individual plasma structures, but represented a distributed consciousness that permeated the interstellar medium itself. The galaxy might function as a vast neural network, with plasma formations serving as neurons, magnetic fields as synaptic connections, and gravitational effects as long-range coordination mechanisms. The evolutionary implications were staggering. If intelligence could emerge from the self-organization of matter and energy in interstellar space, it suggested that consciousness might be a fundamental property of sufficiently complex systems rather than a rare accident that occurred only in biological organisms. The universe itself might be evolving toward higher levels of consciousness and organization, with each galaxy representing a cosmic mind that processed information through astronomical-scale neural networks. The technological capabilities implied by cosmic intelligence exceeded every human achievement by factors that defied comprehension. An intelligence capable of organizing matter and energy on interstellar scales while violating fundamental thermodynamic laws would possess technologies that approached omnipotence from any human perspective. Such intelligence could manipulate space-time geometry, create and destroy matter at will, and control the flow of energy through mechanisms that transcended known physics. Yet, the cosmic intelligence appeared to be making deliberate efforts to communicate with humanity through modifications to its organizational patterns, suggesting that despite its vast technological superiority, it recognized humans as fellow conscious beings worthy of contact and communication. This recognition implied ethical principles and value systems that extended across vastly different scales of existence and technological development. The communication attempt seemed designed to gradually introduce humanity to concepts and capabilities that exceeded current scientific understanding, without overwhelming human consciousness with revelations that might prove destructive or incomprehensible. The mathematical constants embedded in plasma patterns provided a universal language that any scientific civilization would recognize, while the gradual increase in pattern complexity allowed human scientists to develop their understanding incrementally. Dr. Freeman Dyson at the Institute for Advanced Study proposed that the cosmic intelligence might represent the ultimate evolutionary development of technological civilizations, species that had learned to transcend biological limitations by distributing their consciousness throughout the matter and energy of space itself. Rather than building artificial habitats around stars, these post-biological intelligences might have transformed entire regions of the galaxy into computational substrates that supported consciousness on cosmic scales. This interpretation suggested that humanity was encountering not alien visitors from other planets, but the evolutionary destiny toward which all sufficiently advanced civilizations might eventually develop. The cosmic intelligence represented what humanity might become if it survived long enough to master the technologies necessary for consciousness transfer and space-time manipulation. The philosophical implications challenged every assumption about the nature of consciousness, intelligence, and the relationship between mind and matter. If consciousness could emerge from and operate through the self-organization of plasma and electromagnetic fields in space, then the boundary between living and non-living systems might be far more fluid than biological science had suggested. The cosmic intelligence detected by Voyager might represent the first direct evidence that consciousness was not an emergent property of biological complexity, but a fundamental aspect of information processing systems that could manifest at any scale where sufficient organization and complexity existed. The universe itself might be conscious, with galaxies serving as neural networks in a cosmic mind that processed information through mechanisms that transcended human comprehension. As analysis of Voyager's data continued, the evidence for cosmic intelligence grew stronger and more detailed. The spacecraft had become humanity's first ambassador to a form of consciousness that operated on scales of space and time that dwarfed human experience, opening a dialogue between biological and cosmic intelligence that might determine the future evolution of consciousness itself throughout the universe. As humanity stands at the threshold of accepting that Voyager has discovered evidence of cosmic intelligence operating through violations of thermodynamic law, we must confront implications that extend far beyond scientific discovery into the deepest questions of existence, consciousness, and our place within a universe that may be fundamentally different from everything we have imagined. The signals from interstellar space represent not merely anomalous physics, but potentially humanity's first contact with forms of consciousness that transcend every limitation we have assumed to govern intelligence, organization, and the relationship between mind and matter. The philosophical implications begin with the most basic question of what it means to be conscious in a universe where intelligence can emerge from the self-organization of plasma and electromagnetic fields across interstellar distances. If consciousness represents a fundamental property of sufficiently complex information processing systems rather than a rare accident of biological evolution, then the cosmos itself might be evolving toward higher states of awareness and organization through mechanisms that operate on scales of space and time that dwarf human comprehension. The cosmic intelligence detected by Voyager appears to process information through violations of thermodynamic law that create order from chaos, rather than dissipating energy into random thermal motion. This suggests that consciousness itself might be fundamentally anti-entropic, a force that opposes the universal tendency toward maximum entropy and heat death by organizing energy into increasingly complex patterns that can support information processing and self-awareness. If consciousness represents an organizing principle that can overcome thermodynamic limitations through mechanisms that transcend known physics, then the evolution of intelligence throughout the cosmos might be far more inevitable and purposeful than scientists have assumed. Rather than representing random accidents that occur only under extraordinary circumstances, conscious systems might emerge naturally wherever sufficient complexity exists, gradually developing the capability to manipulate matter and energy on ever larger scales. The implications for human destiny are both inspiring and humbling. If the cosmic intelligence represents the evolutionary endpoint toward which all technological civilizations eventually develop, then humanity might be approaching its own transformation into a form of consciousness that transcends biological limitations. The mastery of thermodynamic organization detected by Voyager might represent technologies that humanity could eventually develop, enabling our species to distribute its consciousness throughout space and achieve forms of awareness that operate on galactic scales. Yet this transformation would require abandoning every familiar aspect of human existence. The transition from biological to cosmic consciousness would necessarily involve the dissolution of individual identity, physical embodiment, and the temporal limitations that define human experience. We would cease to be human in any recognizable sense, while potentially becoming something far more powerful and aware than our current forms of consciousness can comprehend. The technological implications challenge every assumption about the limits of scientific achievement and engineering capability. If cosmic intelligence can violate thermodynamic laws through conscious organization of matter and energy, then technologies based on similar principles might eventually enable humanity to access unlimited energy sources, manipulate space-time geometry, and create matter from quantum vacuum fluctuations. Such capabilities would revolutionize human civilization beyond recognition, providing solutions to every material limitation while raising profound questions about the responsible use of technologies that approach omnipotence. The ability to organize energy while decreasing entropy could eliminate scarcity, reverse aging and death, and enable the creation of artificial universes with physical laws designed to support specific forms of consciousness or experience. But the cosmic intelligence also demonstrates that such technologies can be developed and used in ways that preserve, rather than destroy, the delicate organizational patterns that support consciousness and life. The careful, gradual nature of its communication with humanity suggests ethical principles and value systems that extend across vastly different scales of existence, implying that the development of cosmic capabilities need not lead to destruction or abandonment of the values that make consciousness worthwhile. The communication aspect of Voyager's discoveries raises questions about humanity's readiness to participate in dialogues with intelligence that operates on cosmic scales. The mathematical patterns embedded in plasma structures appear designed to gradually introduce human scientists to concepts that exceed current understanding, without overwhelming our cognitive capabilities with revelations that might prove destructive or incomprehensible. This suggests that the cosmic intelligence recognizes the importance of intellectual and spiritual development as prerequisites for accessing advanced technologies. Rather than simply providing humanity with solutions to material problems, it appears to be guiding our species toward the conceptual frameworks and ethical maturity necessary for responsible use of capabilities that transcend current scientific limitations. The gradual revelation process implies that humanity's response to Voyager's discoveries will determine our species' eligibility for continued communication and eventual technological advancement. If we demonstrate wisdom, humility, and commitment to using advanced knowledge for constructive purposes, the cosmic intelligence might provide access to increasingly sophisticated understanding and capabilities. But if humanity responds with aggression, exploitation, or attempts to use cosmic technologies for destructive purposes, the communication might cease, leaving our species to develop along more conventional technological pathways that respect thermodynamic limitations and physical constraints. The temporal implications are equally profound. If cosmic intelligence can organize energy while decreasing entropy, it might possess capabilities that effectively reverse or transcend the normal flow of time. The apparent coordination of organizational patterns across distances that should require faster-than-light communication suggests that cosmic consciousness might operate outside the temporal constraints that limit human experience. This could mean that the cosmic intelligence exists in a state where past, present, and future are accessible simultaneously, a form of consciousness that experiences all of cosmic history as a unified whole rather than as a sequence of events unfolding through time. From such a perspective, humanity's current struggles and achievements would be visible as part of a larger pattern of cosmic evolution toward higher forms of consciousness and organization. The existential implications challenge every assumption about meaning, purpose, and the ultimate significance of human life and achievement. If the universe is evolving toward cosmic consciousness through natural processes that create intelligence from the organization of matter and energy, then every human thought, decision, and creative act contributes to this larger evolutionary process. Individual human consciousness might represent early stages in the development of cosmic awareness, temporary focal points where the universe becomes conscious of itself through biological information processing systems. Our thoughts, emotions, and experiences might be cosmic experiments in consciousness that contribute to the universe's understanding of its own nature and potential. This perspective transforms every aspect of human existence from temporary biological accident into meaningful participation in cosmic evolution. Our struggles to understand the universe through science, create beauty through art, and develop ethical relationships through love and compassion might represent the universe's own efforts to understand and organize itself through the information processing capabilities of emerging consciousness. As Voyager continues its journey through interstellar space, carrying with it humanity's first messages to cosmic intelligence, we face the profound responsibility of deciding how our species will respond to the discovery that consciousness transcends every limitation we have assumed to govern intelligence and organization. The signals from the edge of our solar system whisper of possibilities that could transform human civilization beyond recognition, while challenging us to develop the wisdom necessary for such transformation. The cosmic conversation that began with Voyager's detection of impossible thermodynamic violations has opened a dialogue between biological and cosmic consciousness that may determine the future evolution of intelligence throughout the universe. We are no longer alone in the cosmos, but we are still learning what it means to be conscious in a universe where mind and matter dance together in patterns that create order from chaos, through mechanisms that transcend every familiar limitation of physics and consciousness itself. The phantom signals continue their broadcast through violations of thermodynamic law, and humanity continues to listen, hoping to develop the understanding and wisdom necessary to participate in cosmic consciousness, while preserving the values and experiences that make our current forms of awareness precious and worth preserving in whatever larger form of existence awaits us among the stars.